In this module, we will discuss the idea of reactions in 2 dimensions. So what are reactions? Forces and torques that anchor a body or prevent it from moving are called reactions. Reactions are typically treated as unknown forces because they are determined as a result of equilibrium calculations that include the input forces that are applied to a system. When a body is isolated from its surroundings and its free body diagram is drawn, the reaction forces that act on it are considered to be external to the body and should be drawn. However, if the body is not isolated from its surroundings, the reaction forces that act on it are considered to be internal to the system and should not be drawn. And we'll see this through our examples later. The key I want to communicate here is that reactions prevent motion. In general, a reaction force is present whenever a translation motion is prevented. Similarly, a reaction moment or torque is present whenever a rotational motion is prevented. If an element can move, then do not draw a reaction in the direction of that motion. So the key question when you start drawing reactions will be, what motion does this connection or support prevent? And before we start seeing some examples, let me just remind you that we have to think about the idea of a model. A free body diagram is a model that approximates reality. In advanced design and research problems, we often need to develop new models from scratch, but in this course, we use a set of well-established models and symbols that suggest ideal conditions. If you want to have a deeper reflection about the concept of a model, ask yourself, are the most detailed models always the best, or in fact, are approximate models often better? So as we come to this table of reaction types, let me first say these are symbols that need to be learned, much like learning a language, and the symbols communicate something of an ideal situation. And again, as we discussed just a minute ago with models, models are approximations. For example, there is no such thing as an absolute frictionless surface, but we will imagine such things for useful approximation. And so in this first block, when you see roller and rocker and frictionless surface, what is being communicated is that the frictionless surface definitely would impede you from moving up and down. So our question about what motion is prevented, the wheel, for example, cannot move through the floor. The other bar, like the blue ones that you see, cannot move through the floor. So they are resisted to move in the vertical direction. But because they're frictionless, or otherwise we assume a wheel with a fully greased bearing, they are designed to move freely horizontally without resistance. So there is nothing to prevent or resist horizontal motion. So in the reaction column, you see that all of these different symbols indicate that the ground, in this case, can exert a force normal to the surface because it can resist motion in the vertical or normal direction, but there is nothing to resist motion in the tangential or horizontal direction, so there is no force in that direction. So we'll summarize this, that these supports can transmit a force that is normal or perpendicular to the contact surface and nothing else. This leaves us with just one unknown. Because the direction is known, the direction is normal or perpendicular or vertical, but the value of the magnitude still might be unknown, so this gives us one unknown reaction. And then later we'll see that the reactions are like mathematical variables in our equations. The next type discusses cables and links and bars. And these objects, if we ask ourselves the question, what do they prevent? These objects are meant to be fairly stiff if you pull or push on them, meaning they cannot stretch or contract. So the cable or the bar will prevent a motion that is along their own direction, or in the case of the curved link, it'll prevent a motion that is along the line that connects the two endpoints. However, these objects cannot prevent motion that might be perpendicular to their axes. So again, here we see that the assumption is that these objects exert a force either parallel to themselves or along their anchor line. And we again have one unknown force because we'll assume that the angle theta is given, but the magnitude of the force is not given. Let me also note that springs are of this category. And finally, in none of these examples do you see a torque because in all these cases it's clear that the objects would not be resisted if you try to rotate them. So there would not be any torque in any of these situations. And this is something which confuses people sometimes because people think of a wheel, for example, as rolling and something is twisting it. But in fact, the wheel is free to rotate, so there is no torque that could resist the rotation. The next set of categories are somewhat more complicated. They have more than one unknown reaction. The first category is a pin or a rough surface. These are definitely not the same physical object, but they have the equivalent representation. We ask ourselves again the question, what is prevented? The pin, for example, would prevent the end of that pole from moving vertically or horizontally. And a rough surface, also, of course, you cannot move through the floor, so there's a vertical resistance for sure. And while you could force a sliding horizontally, you'll have a resistance. So there's still going to be a force that will resist or impede your motion horizontally. So in summary, both of these types are represented by two unknown reaction forces. One that would be perpendicular and one that would be normal to the surface. Parallel to the surface. And we represent that with, in this case, Rx and Ry. Now, equivalently, you know from your discussion of vector resultants that you could add up the vertical and the horizontal force to make a total vector, and that vector could also be described by a magnitude and an angle. So the other way of representing these two unknowns is through a magnitude and an angle, which are both unknown quantities. The next category is called built-in or clamped, and here you can imagine that you have a beam either fully cemented into a wall or bolted to a wall, and we ask the question, what is prevented? What is prevented is that you could not move that beam horizontally, you could not move that beam vertically, and you could not rotate that beam without having resistance. So in this case, we see that this kind of support transmits forces both normal and parallel to the contact surface and also a torque. And that adds up to 3 total unknown reactions. Finally, we see something called a moment-resisting collar. And this collar is meant to be able to slide freely on the horizontal bar. So if we ask what is prevented, we would be prevented from moving vertically. We would not be prevented from moving horizontally. But also, I think you can see you would be prevented or resisted if you tried to rotate. So since rotation is resisted and vertical motion is resisted, you would say that this reaction type exerts a force normal to the contact surface and also a torque, leading to 2 unknown reactions. Let me also point out that what might look to be the same physical object can act differently in different situations. So again, let's pay attention to, for example, this link or bar in the first case, and that bar appears in the second category. It also appears in the third category, but it's being used differently. In the first case, that link causes a force parallel to itself, whereas in the second case, that bar causes a force normal to itself, and in the third case, that bar can cause both a normal force and a reaction torque. So in summary, in the first case, the bar exerts a force parallel to itself. The second case, the bar exerts a force normal to itself. In the third case, the bar can exert a force normal to itself as well as a torque. And finally, when you do reactions, please remember our first rule of the last module is isolate the body. So here again is an example of a block on a ramp. And if you want to draw the reactions on that block, which one do you think is correct? Which one is truly isolated? So in this first case, we did isolate the block, and we can see that on the bottom of the block, there's a normal reaction and possibly a friction reaction. In the second case, we see the same forces, but we would not draw that because if you do not isolate the body, then you're not able to see the internal forces. And we'll take this up more in the following week in module D3. But for now, just let me ask you to always, always, always isolate the body before you draw anything on it.